Hello, and welcome back to another statistics video. In this video, we are going to focus on something called bivariate data. So when we talk about bivariate data, we're talking about data that really is coming in ordered pairs. So we could think about it in terms of x coordinates and y coordinates. And we're going to have a set of these x and y coordinates, and we're really asking the question, is there some kind of linear relationship between those values? So let's look at a couple of graphs. The best way to be able to do this would be to take those data points and create that scatter plot. So we're going to create a scatter plot with all the values, and we're looking for patterns. It does not have to be this perfect straight line. It would be wonderful if it was, but most of the time it's not going to be. So if we were to look at these examples here, that first one, we've got a lot of points that look like they are linear in function. So we would say that this looks like it's going to have a strong linear correlation. And because it's increasing left to right, we would say that's going to be a positive linear correlation. If we look at that second picture, we see that everything does look linear, but it's decreasing. So we would say that it is a negative correlation. And that negative and positive is going to relate back to this idea of slope. If you remember back to an algebra course, we had y equals mx plus b. M was the slope of the equation, and b is the y-intercept of the equation. So our goal is to take our ordered pairs, plot them. We're hoping for some kind of linear relationship. Either we're going to have a positive slope or a negative slope. If there's a relationship. Let's look at these other three. If we look at the second one, does that look like it's linear in nature? I would say no, that is not linear. Now, it does look like there's some kind of relationship going on, maybe a parabolic relationship, but it's definitely not linear. And in this section, we are focused on linear functions. What about that third one? Do you think there's a relationship there? I would say no. There is not a linear relationship. To me, it looks like it could be a cubic relationship. And you can analyze things that are quadratic in nature or cubic in nature. But remember, we are focused on linear. And then if we look at that last one, notice how close those dots are, actually how sporadic, really, those dots are. So I would say that there's no linear relationship in that example either. So let's look at some common errors that happen when we start talking about bivariate data. The first one is correlation does not imply causation. Just because there's a correlation between the two doesn't mean one variable forces the other to happen. There could be other things working in the background and that's causing an effect there, and we call those lurking variables. Also, data based on averages. Remember, if we average things together, especially with mean, we suppress outliers. So that could affect our correlation coefficient. And remember, if there's no linear relationship, it's possible there could be some other relationship going on, such like a quadratic that we saw in one of the previous scatter plots we had. So it's always a good idea to draw a scatter plot first to see whether or not there's going to be a relationship between our variables or a possible relationship. So let's dive into more about that linear correlation coefficient. This is called Pearson's correlation coefficient, and we use the R to um, look at that. That's the representation for that, the symbol there, if you will. So R, the linear correlation coefficient, measures how strong that linear relationship is between those two variables. Now, that R value will always be between -1 and 1. And really, the value of R depends on the slope. If our slope is positive, that means our line is increasing, which means that R is going to be positive. If the slope is negative, that means the line is decreasing, which means R is going to be negative. So the sign of R is is in relation to the sign of the slope. But that R value will always be between -1 and 1. -1 and 1. If we get 1 exactly, we have a perfect correlation. This is going to be a positive line, and all the points are going to line up perfectly. If we end up with -1, then we're going to have a negative correlation, and again, those dots are going to be perfectly in line. If we end up with 0, there is no correlation. And that means it's just going to be, those dots are going to be all over the place, like in that last picture that we had here. Now, we're going to use technology to find these values, but there are formulas associated with finding the correlation coefficient. So just to show you what one of those formulas would look like. We wanted to find the correlation coefficient. We could take the sum of each x minus the mean of x's times the y minus the mean of the y's. So we'd add all those up, divided by the square root of each x minus the mean quantity squared, add all those up, find the y's minus the mean of the y's, square those, add all those up, and then multiply those together. And then, don't forget the square root in the bottom. So the formulas are not very nice, but the technology is going to make this really, really just simple for us. Okay, what's really interesting about R is that if I were to flip-flop the X's and the Y's, the R value is going to stay the same. Okay, but R is very sensitive to outliers, and in fact, one outlier can drastically change what that R value is. Now, we can also find something called the coefficient of determination, and that is literally the correlation coefficient squared. That represents the proportion of the variation in the y's that can be explained by the linear relationship between x and y. So what does that measure? It actually measures how well the least squares regression line describes the relationship between the two variables. The closer r squared is to 1, the better that line is going to describe how x affects the value of y. So x is your independent variable, so we want to know how the independent variable affects the dependent variable of y. R squared is always going to be a positive value because I'm taking some number and I'm squaring it. So let's look at some pictures of correlations. Look at that first picture. This is a perfect correlation. Notice all those dots are perfectly lined up. This last one is a perfect negative correlation. Notice they're all perfectly lined up again in a straight line, and they are decreasing when I go from left to right. So this has an R value of -1 because I'm going to have a negative slope, whereas that first picture has an R value of +1 because I have a positive slope. So if I were to look at the second picture here, positive correlation, okay, the dots are not in a perfect line, but they're still pretty close together. So we would expect that R value to be pretty close to 1. If I were to look at this one, picture E, notice I have a negative correlation, but the dots are still pretty close together. So we would expect that R value to be close to -1, and it is. In C and F, we have moderate correlations. And in G, we have no correlation at all. We just have a whole bunch of dots that just look like they've been thrown randomly on the graph. There's not any relationship that I could see there. But in this last one, it's not linear, but it looks like there could be some type of other relationship that we could explore. But this is not a linear graph at all, so we would expect that R value to be close to 0. So what is our test for that linear relationship? Well, our textbook is going to use the following. If everything is based on R, so we're going to find R, and we're going to use technology to find R. We're going to say that there is a strong linear relationship if the absolute value of R is greater than 0.8. So if I get something like 0.85, I'm going to say this is a really good fit. This is a strong correlation. We're going to say it's moderate if we get something between 0.5 and 0.8. So let's say we get R is equal to 0.63. We're going to say that is a moderate fit. If we get R is negative 0.57, we're looking at the absolute value of R here. So that absolute value would be positive, and 0.57 does fall within that interval. So we would say this would be moderate. And then we're going to say that we have a pretty weak correlation if the absolute value of R is less than 0.5. So if we have R is equal to 0.20, we're going to say it's weak. Or if we're going to get R is equal to negative 0.34, again, we're going to say this is weak because that absolute value is less than 0.5. So let's look at a few examples. We have 8 sets of mothers and daughters. The linear correlation coefficient is found to be 0.693. So 0.693 falls in our moderate range. So we would say there is a moderate correlation there. If we look at this one, we have 62 households. The linear correlation coefficient is 0.758. So 0.758 also falls in that moderate relationship, that category.